Hello, my dear students. Now you are all familiar with hydrograph, synthetic hydrograph, etc. Now let us discuss about instantaneous unit hydrograph. We have seen earlier that each unit hydrograph representing 1 centimeter of direct runoff is for some unit duration T0. For a catchment, there can be a number of unit hydrographs corresponding to various values of unit duration T0. To obtain the runoff hydrograph resulting from a storm of varying duration and varying intensities, it is preferable to have a unit hydrograph of very short duration. Theoretically, the shortest unit duration is 0. If the duration of the rainfall excess becomes infinitely small, the resulting unit hydrograph is called instantaneous unit hydrograph. Thus, instantaneous unit hydrograph is a fictitious conspectual unit hydrograph which represents surface runoff from the catchment due to an instantaneous precipitation of rainfall excess volume of 1 centimeter. The instantaneous unit hydrograph or IUH is designated as U of T0 or simply as U of T. You can see this is a graph of various different unit duration time T0, and this is the discharge. Okay, so these are the unit hydrographs for the various duration. This is for T1, T2 and T3. Okay, so this is nothing but a hydrograph produced by an effective rainfall of 1 mm and having an infinite reference duration. Okay, so now let us see how to calculate or how to find instantaneous unit hydrograph. Instantaneous unit hydrograph can be easily derived from S-curve hydrograph obtained from an available unit hydrograph of duration T0. If two S-curves are drawn at a time lag of T0, the ordinate of unit hydrograph of T0 or unit duration at any time T is given by this equation U of T, T0 equal to T0 divided by T0 into St minus St minus T0, where U of T T0 is the ordinate of unit hydrograph of unit duration T0. T0, capital T0 is the unit duration of unit hydrograph from which S curve has been obtained. St is ordinate of S curve at any time T, and S of T minus T0 is the ordinate of shift S curve shifted by T0. So, instantaneous unit hydrograph can be obtained by using this formula. U of T is equal to T0 into D of St whole to the power T0 divided by Dt. That is nothing but 1 divided by R0 into dSt to the power T0 divided by dt, or you can write the ordinate of instantaneous unit hydrograph at any time t is equal to T0 into the slope of S curve derived from T0 or unit hydrograph at time t. Okay, in this equation here, in this equation, R0 is the intensity of rainfall excess, which is given by R0 is equal to 1 divided by T0. If R0 is equal to 1 centimeter, then you will get this equation as U of T is equal to D of St divided by dt, where St is the ordinate of S curve of intensity 1 centimeter per hour. Thus, the ordinate of instantaneous unit hydrograph at any time t is the slope of the S curve of intensity 1 centimeter per hour. Okay, this is about instantaneous unit hydrograph. So I hope all of you understood the detail. The description or explanations are given in the textbook. You can refer the textbook. Okay. Now let us discuss about the flood routine. What is this flood routing? The flood hydrograph is in fact a wave. The stage and discharge hydrographs represent the passage of waves of stream depth and discharge respectively. As this wave moves down, the shape of the wave gets modified due to channel storage, resistance, lateral addition or withdrawal of flows, etc. When a flood wave passes through a reservoir, its peak is attenuated and the time base is enlarged due to the effect of storage. The reduction in the peak of the outflow hydrograph due to storage effect is called attenuation. Further, the peak of outflow occurs after the peak of the inflow. The time difference between the peaks of inflow and outflow hydrographs is known as lag. Modification in the hydrograph is studied through flood routing. So, flood routing is the technique of determining the flood hydrograph at a section of river by utilizing the data of flood flow at one or more upstream sections. So, it is nothing but a technique of determining the flood hydrograph at a section by utilizing the data of flood flow at one or more upstream sections. Well, let us see what are the concept of flood routing. Flood routing is a process used to predict the temporal and spatial variations of a flood hydrograph as it moves through a river reach or reservoir. Flood routing is used to predict the magnitudes, volumes, and temporal patterns of a flood hydrograph as it translates down a river reach or reservoir. The effects of storage and flow resistance within a river reach are reflected by changes in hydrograph shape and timings as the flood wave moves from upstream to downstream. In general, routing methods are classified as hydrologic and hydraulic, depending respectively on whether the methods are based on empirical or physical process equations of motions. There are different methods of routing, flood routing. The main methods are these: modified pulse, kinematic wave, Muskingum J, and dynamic. The first one is a modified pulse. So the modified pulse routing method is probably most often applied to reservoir routing. The method may also be applied to river routing for certain channel situations. The modified pulse method, also referred to as the storage indication method. The heart of the modified pulse equation is found by considering the finite difference form of the continuity equation. Next one is kinematic wave. Kinematic wave channel routing is probably the most basic form of hydraulic routing. This method combines the continuity equation with a very simplified form of the Saint-Venant equations. Kinematic wave routing assumes that the friction slope is equal to the bed slope. Additionally, the kinematic wave form of the momentum equation assumes a simple stage-discharge relationship. Next one is Muskingum nodes. The method assumes a single stage discharge relationship. In other words, for any given discharge Q that can be only one stage height, this assumption may not be entirely valid for certain flow situations. For instance, the friction slope on the rising side of the hydrograph for a given flow Q may be quite different than for the recession side of the hydrograph for the same given flow Q. This causes an effect known as hysteresis, which can introduce errors into the storage assumptions of this method. The next method is Muskingum Conjay. Here, this formulation is similar to the Muskingum type formulation, and in this type, the Muskingum-Gundry derivation begins with the continuity equation and includes the diffusion form of the momentum equation. These equations are combined and linearized, and this equation is given by like this. Okay, here where Q is the discharge, T is time, X is distance along channel, Qx is lateral inflow, C equal to wave celerity, and M is hydraulic diffusivity. Last one is full dynamic wave equation. The solution of the Saint-Venant equation is known as dynamic routing. Dynamic routing is generally the standard to which other methods are measured or compared. The solution of the Saint-Venant equation is generally accomplished via one of the two methods. The first one is the method of characteristics, and second one is the direct method, implicit and explicit. It may be fair to say that regardless of the method of solution, a computer is absolutely necessary as the solutions are quite time consuming. Next, let us see what are the applications of flood routing. For accounting changes in flow hydrograph as a flood wave passes down, it can be used for flood forecasting, flood protection, and flood warning, and also for the design purpose, that is water conveyance, spillway systems, protective measures, hydro system operation, and also for the water dynamics for this under ungauged rivers, peak flow estimation, and river aquifer interaction. So these are the some of the applications for reservoir routing and channel routing. This is reservoir routing and this is channel routing. I hope all of you understood. Thank